Okay, so at the very end of last lecture I wrote down that hk dirham of x of the complex numbers is isomorphic to the direct sum over p plus q is k of hp comma q e bar of x when x is compact scalar. Another useful fact, which I didn't write down before the break, is that the relationship between the harmonic PQ forms and the harmonic QP forms is that the if you take the complex conjugate of the harmonic PQ forms, it's equal to the harmonic QP forms. Also, so things in here of the form alpha plus I beta, and then the complex conjugate is alpha minus I beta. So harmonic, and this is because by the Kähler identities, d bar star plus d bar star d is d star plus d star d. So this, well, this is the kernel of this, and therefore the complex conjugate is the kernel of that, but they're equal. So that was part of the Kähler identities. But now this was these are isomorphic to the Dolbeau groups. So hence h d bar p comma q of x complex conjugate is, well, isomorphic to qp d bar of x. So that's a relationship between two different Dolbeau groups in general. Again, for x compact Kähler. I don't think that's true in general. Okay, so so these have some topological consequences. So for example, this tells you that h 2j of x comma c is the direct sum over p is 0 up to j of an h p comma 2j minus p of x. So I mean that. Now let's say j minus 1. Have I done something awful? No, yeah, well, I'm sorry. I'm going to take 2j plus 1 here. Go up to j, 2j plus 1 minus p. So I'm taking the first half of these, direct sum. Now, the second half, I'd take p to be larger than half the dimension, but instead I can take direct sum, again from p is 0 up to j, of h p 2j plus 1 minus p of x, but now I'm going to take the complex conjugate there. So you take that thing, and then you for all the things with p greater than half the dimension, you replace it by the complex conjugate and swap the p and the q round. So these two things are the same vector spaces, but complex conjugate. So, well, the b 2j plus 1 of x is even. So the odd Betti numbers of x, or the Betti numbers of x with odd index are even for x compact Kähler. So any compact complex manifold you find which has an odd Betti number which is odd can't be Kähler. Okay, so for example, if you were to take S3 cross S1, That's a 4-manifold. You can realize it as a complex manifold by taking it to be C2 take away 0 divided by the integers acting by dilations. You could say kind of 2 to the z, if you like. That is the dilations of, by multiplication by 2 to the n for n in the integers. It's a complex thing. This is a compact and complex. I think it's called the Hopf surface. With B1 equals 1. So it can't omit a calorimetric. Okay, so this is a compact complex manifold which can't have a calorimetric. This also implies that it can't be a complex projective manifold. So this is a complex manifold which you can't embed into any complex projective space, because if you could, then it would have a calorimetric by restriction. Okay. So next, let's move on. Section 3.5 on the Kähler cone. So I want to give you some kind of idea of what is the family of calorimetrics on some given compact complex manifold, supposing it has any calorimetrics at all. So let's, actually we don't need compact at this point, so let's X and J be a complex manifold. Later we might take it to be compact. So then calorimetrics G on X correspond to Kähler forms little omega on X. The metric corresponds to the 2 form. You construct omega from G, but you can also reconstruct G from omega. Well, a 2 form little omega, any 2 form, real 2 form omega on X is the Kähler form of a calorimetric G on X with its complex structure, and G is then unique. So if 3 conditions hold, well, so firstly, omega lies in well, the real 2 forms on X, lambda 2 T star of X, intersected with lambda 1, 1 T star of X, where the intersection is in lambda 2 T star of X tensored over the reals with the complex numbers. So I'm thinking about real 2 forms here as being contained in the complex 2 forms as the ones with imaginary part 0. So that is little omega is a real 1, 1 form. That's the first condition. The second condition is that d omega is 0. So omega is closed. And then the third condition is that, well, omega, let's say at some point little x of a v and then JV is positive, and that has to be true for all little x in big X and V in the tangent space to x, big X, little x, which are non-zero. So for every non-zero vector, omega of V against JV has to be positive. So that's the positive definite conditions. So we say omega is positive definite. Okay, so those are necessary and sufficient conditions for omega to give you a Kähler metric back. So let's note that conditions 1 and 2 are linear conditions on little omega. So the set of solutions to them will be a vector space. And 3 is an open condition. Well, open, let's say, in the C0 topology upon 2 forms omega, which is also convex. So these omegas satisfying 1 and 2 lie in a vector space, and then the set of solutions to 3 is a convex subset of that vector space. Actually, it's a cone. So if little omega 1 and omega 2 satisfy 1 up to 3, and let's say lambda 1 and lambda 2 are non-negative real numbers with their sum, lambda 1 plus lambda 2 is greater than 0, so at least one is positive. Then lambda times omega 1 plus, sorry, lambda 1 times omega 1 plus lambda 2 times omega 2 also satisfies 1 to 3. So thus, the set of Kähler metrics on a fixed complex manifold X and J is a convex cone. A bit later on, we'll see that it's actually infinite dimensional because there's always lots of solutions. And well, if we wrote condition 2 as nabla omega equals 0 instead of d omega equals 0, then it would not be linear. Because the operator nabla depends upon g, which depends upon omega. So nabla itself depends on little omega. So considered as a partial differential operator on omega, this is actually nonlinear. Okay. Next, well, if we let x and j and g be a Kähler manifold, with Kähler form omega. So then, well, d omega equals 0. So we can form the de Rham cohomology class, square brackets omega, lies in the H2 de Rham of x over the reals. So we always get an interesting cohomology class out of our Kähler metric. Now, if X is compact, then the de Rham cohomology groups have splittings into the Dolbeau groups by what we've just said. So if X is compact, then, well, we have H2 of X de Rham, at least over the complex numbers, splits as an H20 d bar of X plus an, well, let's leave the d bars out, an H11 of X plus an H02 of X. And omega lies in the 1,1 part of this, so square brackets omega lies in, well, H2 of X comma R intersected with H11 of X, where the intersection is in H2 de Rham of X C, which we consider as containing both the real de Rham cohomology and these complex vector subspaces. So, right, and we call square brackets omega the Kähler class of G. Okay, actually, the Kähler class gets used to mean two slightly different things. Sometimes by the Kähler class, you mean the de Rham cohomology class, omega, square brackets omega. Sometimes by the Kähler class, you just mean the set of all Kähler metrics realizing a fixed cohomology class. So you might say G1 and G2 are in the same Kähler class if omega 1 and omega 2 are in the same de Rham cohomology class. So both things get used like that.
By complex de Rham, do you just mean real de Rham tensored with Q? Tensored with C?
Yes, or you could form it using complex forms. Yeah, it's basically an alpha plus I beta where alpha and beta lie in the real de Rham. Yeah?
Does this have anything to do with the second trig class?
No, don't think so. The Ricci curvature will have something to do with the first Chern class, which we'll see on Monday, I think. But no, the Kähler, this can be anything it likes. It's not constrained by any characteristic classes. Okay, so the set of Kähler classes on X is the Kähler cone Kähler K sitting inside, or let's say okay, and well, if X is compact, it is an open and convex cone in H2 de Rham of X R intersected with H11 of X. If X is not compact, it's still a convex cone in H2 of X de Rham, but you're not sure exactly what you mean by this, and you need to worry about what topology was going on before you could say it was open. Okay. So, and it can be interesting to work out what K is in examples. Very often it's a kind of polyhedral cone. So it would be defined by, so you have some vector subspace here, and then K might be defined by a number of strict inequalities by, well, so for example, if you have a holomorphic curve sitting inside X, the area of that has to be positive for any Kähler metric. That will give you a linear inequality, which K has to, gives you a hyperplane which K has to lie on one side of. Quite often, K would just be on one side of some finite number of hyperplanes, but not always. So Kähler cones can be quite complicated. Okay, now there's something called the DD bar lemma. Well, so there's two versions. There's a local one and there's a global one. I'm going to put them both in the same result as parts A and B. So part A would say that, let's suppose big U in C to the M is an open set, and I don't want there to be any interesting topology, so let's say it's open and contractible. So it could be just an open ball, for example. And omega is a closed and real 1,1 form on U. So because U is contractible, its second cohomology is 0, so being closed implies it's also exact. So you could write it as D of something, but we do something stronger than that. So then omega is actually I times d bar of f for some smooth f going from x into the reals. Okay, so if you work it out, you'll find that IDD bar is a real operator. It takes real things to real things, and the I is there to, if without the I it would be an imaginary operator. So f is a real function, therefore omega is a real form.
I think you mean U, F U to R.
Oh, thank you. Yes, you're right. Okay. Now, okay. Well, this is also d of brackets I d bar of f, because d is curly d plus curly d bar, and curly d bar squared is 0. So, I'm writing omega. Well, so I've said it's closed, so therefore it's exact because U is contractible. So we know we can write omega as d of some 1 form. That would be a first integral. This is really a second integral. It says we can take the 1 form to be of the form I d bar f for a function. Okay, so this is saying that you can integrate omega once more than you were expecting to. There's also a global version of this, B. Now let's suppose x comma j. Well, really I want to say a compact Kähler metric manifold, but it's better to say is a compact complex manifold admitting Kähler metrics. So, because the statement I'm going to make doesn't use the Kähler metric, but nonetheless, it won't be true for some compact complex manifolds which don't have Kähler metrics. And let's say that omega is a closed and real 1,1 form on X. Doesn't have to be positive definite, doesn't have to be the Kähler metric of a Kähler manifold, of a Kähler form of a Kähler metric. In fact, it won't be, because I'm going to require that square brackets omega equals 0 in h2 diram of x are. Actually, yeah, so just back here, well, yeah, okay, I'll say something later. Okay, so if you have a closed real 1-1 form which is exact, and so 0 in de Rham cohomology, then the conclusion is that, again, little omega is I curly d bar of f for some smooth f going from x into the reals. And in this case, we can actually say something a bit more. The f is unique, well, not completely unique, but up to addition of a constant, f goes to f plus c for c in the reals. Okay, well, that's if x is connected. If x is not connected, then you get to add a constant for each connected component of x. Okay, so this is a powerful fact. So some conclusions from this. Well, firstly, if you take any Kähler manifold, compact or non-compact, and you take a small open subset in it, you can identify that with a small contractible open subset. You can identify it with a subset of C to the m. And then you'll see from part A that every Kähler metric has Kähler form locally of the form little omega is I d bar f for f going from x into r smooth. Well, okay, so if we're working locally, it's not defined on all of x, so locally defined, meaning just defined on some open subset in x, and with second derivatives satisfying a positive definiteness condition. Okay, so I told you earlier that the Kähler forms of Kähler metrics satisfy three conditions, 1, 2, and 3. Omega is I d bar f will satisfy conditions 1 and 2 automatically because, well, it's closed because it's d of I d bar f as that, and it's of type 1, 1 because you start with f, which is a 0 form. You take a d bar, which makes you into a 0, 1 form, then take a d, which makes you into 1, 1 form. And it's real, because f is real, and that's a real operator. So this is a closed real 1, 1 form automatically. And then the third condition is that omega should have some positive definiteness condition, which is this bit here. Okay, so a metric is a kind of complicated thing. It's got, half n squared plus n functions inside it, but in this case, Kähler metrics can always be written down in terms of a single function, which kind of makes them easy to work with. When you want to think about Kähler metrics satisfying some PDE, it's helpful to write the Kähler metric in terms of the function, and then you end up with just PD on a function instead, which can be a lot easier to do. So secondly, if we let X and J and G be any Kähler manifold with Kähler form omega. So then, for any smooth f going from x into the reals, which is sufficiently small in, well, C2. Well, so actually, basically, if you take the second derivatives of f, the speculative connection, you take their C0 norm, and if you make that to be less than some constant, it may be 1 or a half or something like that, that will do. So then, if you define omega twiddle to be omega plus I d bar f, this is the Kähler form of another Kähler metric G twiddle on X. So what's going on here is that, well, omega is by definition a closed real 1-1 form. That's also a closed real 1-1 form, just obviously. So omega twiddle is closed real 1-1. So to make it the Kähler form of a Kähler metric, this has to satisfy the positive definiteness condition. Now omega already does, and we're just, if this is small enough, then that won't change the positive definiteness. Here, well, we need f small in C2 so that twiddle omega satisfies the positive definiteness condition. So basically, if you think about these as kind of matrices, then with respect to G, which defines omega, omega has eigenvalues 1. And so as long as the eigenvalues of this thing are all strictly less than 1, when you add them up, you'll get positive eigenvalues for this thing. And this kind of conditions is what you need to say all the eigenvalues are less than 1. Okay, so a conclusion is that because there's an infinite dimensional family of smooth functions f you could input here, hence you get that Kähler metrics come in infinite dimensional families in a non-trivial way. And these metrics for different f, and if f apart from the f differing by addition of constants, these metrics for different f are really different, and then they're not typically they're not isometric under some automorphism of x. They really are different, and that's true on any positive dimensional Kähler manifolds. So there are just loads and loads of Kähler metrics, and the same thing won't be true for the other column roots we're interested in. Let's say on compact manifolds, metrics will along me SUM, SPM, SPM, SP1, G2, spin 7 all occur in finite dimensional families modulo diffeomorphisms of the base. But Kähler metrics, there's a kind of infinite amount of variation. Okay, so here we call the function f, which we're doing IDD bar of, a Kähler potential. Either if we're doing it to make the entire Kähler form, or if we're doing it to shift one Kähler form to a different Kähler form. And this is a very useful way of defining Kähler metrics. So I told you before that any projective complex manifold, anything you can realize as a complex submanifold of a projective space, has one Kähler metric, namely the restriction of the Fubini study metric on CPN to it. Now you can see from this that every such complex manifold has an infinite family of them, given by varying the Kähler potential. Okay, so thirdly, if X and J is compact and G and G twiddle are two Kähler metrics, on X in the same Kähler class, that is, their Kähler forms have the same cohomology classes in de Rham cohomology, then omega twiddle is equal to omega plus I d bar of f. So omega twiddle and omega are the Kähler forms of those guys. For some smooth f going from X into R, unique up to addition of constants, f maps to f plus c. So that came from the applying the second part, B, the global DD bar lemma, to omega twiddle minus omega, which has de Rham cohomology class 0 because omega twiddle and omega are cohomologous. Okay, so therefore this condition part 2 actually gives well, all metrics in a fixed Kähler class. That is, all metrics in the given Kähler class on X are of the form, have Kähler forms of the form omega twiddle is omega plus I d bar f. Although, if you want to get all of them, you can't really say you want f to be small anymore. But anyway. Okay, well, the next topic will be Ricci curvature of Kähler manifolds, but I think that's all. Well, let me make one more comment, and then we'll finish a bit early for today. So, well, if X and J and G is a Kähler, and M is the complex dimension of X, so then 1 over M times omega to the M is the volume form of omega. So omega to the m, that means omega, wedge, omega, wedge, wedge, omega, m times. So if X is compact, complex manifolds are, so the volume form of G, so you get a volume form from the metric and the natural orientation on X induced by the complex structure. So given any complex manifold, you can find an orientation on it such that at a tangent space at a point, you take a basis of the complex vector space. The tangent space is a complex space, and so that will give you an E1 up to EM, and then you take E1 up to EM, followed by IE1 up to IEM will give you a real basis, and that would, if you call that an oriented basis, that gives you an orientation. Okay, so if X is compact, then the volume of X to a Riemannian manifold is 1 over m factorial times the integral over X of omega to the m. But the volume is always positive, provided dimension of X is positive. But this is 1 over m factorial times the fundamental class of X in homology, dotted with the de Rham cohomology class of X kind of cupped with itself m times. So this is in H2m of X, and this is in H upper 2m of X. And hence the cohomology class of omega is non-zero in the de Rham cohomology group. Something can only be a Kähler class if its cohomology class is non-zero, and in fact if the mth power of that cohomology class gives you something positive when you integrate it against the fundamental cycle of X. So that's another constraint on the possible cohomology classes of Kähler metrics. Okay, so let's stop there.